Hi, my name is Isabel Cachola. I'm a PhD student at Johns Hopkins University, and I'm here to present to you today TLDR, Extreme Summarization of Scientific Documents. So a quick overview before we jump into things. I'm going to talk a little bit about our motivation for this project and the problem definition, and then I'm going to talk about the data that we used, as well as our modeling, and finally our evaluation. So first, let's tackle motivation and problem definition. So if you're looking at this list of papers and you're a scientist wondering, what should I read? What are you going to do? So first, you might look at the titles of these papers. But the problem is that titles aren't always actually informative to the contents of the paper. And sometimes authors will even write these titles to be a little bit more catchy than informative. You could look at the author list and see if you recognize any of the authors, but this is subject to bias and sometimes favors certain institutions or people. And then finally, you can read the abstract. Now, abstracts are informative to the content of the paper. However, they are too long to realistically read in bulk. On average, abstracts are about 150 words in length. And so if you're a scientist who's really trying to keep up with all of the different incoming literature, this might be too unrealistic for you to read. And so we introduced TLDR Generation. So what is a TLDR? TLDR stands for Too Long Didn't Read. It focuses on the main contributions of the paper, and it is short, 15 to 30 tokens in length, as opposed to the 150 tokens of an abstract. And scientists already use TLDRs in practice. It's very common for whenever a scientist is sharing a new paper of theirs on social media, they'll also include a TLDR of that paper to help people understand what their paper is about before they start diving into the nitty-gritty technical details. So here's an example TLDR. Here we have the snippets from the abstract, introduction, and conclusion of a paper, as well as the author-written TLDR. So this TLDR reads, we develop a new topological complexity measure for deep neural networks and demonstrate that it captures their salient properties. And what you'll notice is that this TLDR pulls keywords from across the entire length of the paper. And so our goal is to train a model that automatically generates these TLDRs from the text of a scientific paper. So now let's talk a little bit about the data. So with this task, there are a few challenges for collecting data. The first is that writing TLDRs for scientific papers inherently requires expertise. Ideally, what we would do is we would take a bunch of papers, hand them to some scientists, have them read the papers in full, and then write TLDRs that summarize that paper. However, this is both time-consuming and it would be expensive to hire these subject matter experts. So where do we go from here? So what we did to collect data is we looked on openreview.net, and OpenReview actually has their authors collect TLDR or write TLDRs for the papers they're submitting. So we use the OpenReview API to collect the author-written TLDRs. However, we felt that this wasn't quite enough data for this task. And so in order to collect additional data, what we did is we collected the peer review comments that are available through the OpenReview API. Now, peer reviewers, whenever they are writing their review for a paper, they'll often include summaries of the papers that they're reviewing in their comments. So we had our annotators read these comments and rewrite them into a TLDR-like form. And this saved us a lot of time and allowed us to collect more data because our annotators only had to read peer review comments, which are much shorter than full length of a paper. So using this method, we are able to collect about 5.4K TLDRs, and we publicly released this data. So let's talk a little bit about the modeling. So there are some unique challenges to modeling this task. The first is the limited size of training data. Even with the data that we collected, modern machine learning techniques are very data hungry, and it still wasn't quite enough data for us to get the results that we wanted. And the second is the need for domain knowledge. TLDRs are inherently domain specific to the papers that they're summarizing, and so this provides a unique challenge for our models. So how did we address this? We introduced a new training strategy in which we train with title generation as a scaffold task. So this is how it works. We took our data set of paper and TLDR pairs and an additional data set of paper and title pairs. We appended codes to the source of those data sets, shuffled data, and then trained BART, which is a state-of-the-art summarization model on that data. And we call this training strategy CATS, Controlled Abstraction for TLDRs with Title Scaffolding. Now, the reason we decided to use title generation as our scaffold task is titles are both short and they contain salient information about the paper. So although they are not TLDRs, they are similar enough to TLDRs that we thought that it would make an appropriate scaffold task. In addition to that, this also addresses our problem of limited training data because titles are widely available and they're, every paper has a title, so it's an easy data to collect. So finally, let's talk about evaluation. So we use Rouge as our automatic metric. Rouge is a measure of overlap between the reference and the generated summaries. And we compared our training strategy against strong baselines. And what we found is that our training strategy outperformed strong baselines on this Rouge metric. However, we know that these automatic metrics aren't perfect, so it's also important for us to do a human evaluation as well. So with our human evaluation, there were two primary questions that we wanted to ask. Are the generated summaries informative, and are they factual? So let's tackle that first question. Are they informative? In order to measure informativeness, we found 6 different nuggets of information that people tend to look for in a summary. So that's area, field of study, or field or topic of study, problem or motivation, mode of contribution, details or description, results or findings, and value or significance. And what we did is we had our annotators go through our generated TLDRs and count the number of nuggets within that TLDR. And what we found was that on average, our generated summaries from our training strategy had a similar number of nuggets to the best baseline. And it also had a similar number of nuggets to our gold TLDRs or the human written TLDRs. So we concluded that our training strategy was similarly informative to the strongest baseline and to the gold TLDRs. Now the second question, are the generated summaries factual? So with this evaluation, we have a similar problem that we had in data collection, and that evaluating the correctness of a TLDR requires careful reading and understanding of the source paper. And again, we're really trying to avoid having our annotators read papers in full because this would just be time consuming and expensive. So here's what we did instead. We took our TLDRs and emailed them to the first or second authors of the original papers. And the assumption here being is that no one knows the papers better than the original authors themselves, and they would be good judges of the factual correctness of our TLDRs. And then we asked them to rate the TLDRs on a scale of 1 to 3, from false or misleading, partially accurate, to mostly correct. And we performed this evaluation on both our strongest baseline and our training strategy. And what we found is that both models received an average rating of 2.5. So we concluded that our model was similarly factually correct to the strongest baseline. Now, our TLDRs are now implemented on Semantic Scholar as a beta feature. So you can go ahead and find this on Semantic Scholar on search pages for computer science papers. Previously, what was here before was the first sentence of the abstract. And now we can see the generated TLDRs for these papers. So to recap, the contributions from this project were we designed a novel data collection protocol that allowed us to collect more data. And then we designed the training strategy to improve results on both automatic metrics and human evaluation. And finally, TLDRs are currently available as a beta feature on Semantic Scholar. So this is work that I did in collaboration with Kyle Lowe, Armand Cohen, and Dan Weld and the Semantic Scholar team at the Allen Institute for AI. And if you were interested in this project, I'd just like to take a moment to plug some of my other recent works. I've done some work on the accessibility of scientific documents and explainability and medical code prediction. For more details on this project, I'd like to direct you to our paper, TLDR Extreme Summarization of Scientific Documents, as well as the TLDR landing page on Semantic Scholar that gives you a little bit more details about this project within Semantic Scholar. Our GitHub is also publicly available, as well as our data. And finally, feel free to contact me through email or check out my website. Thank you.